Thank you for the opportunity to give a talk on a recent work that we have been doing, and we put it out on archive. So this is a work done with my collaborators at Texas A&M with Professor Bhaskar and Professor James. So to give a very brief motivation of what we want to look at. So basically physics before the BBN, let's say the T greater than MeV, is not very well understood due to the lack of observational data. And gravitational waves can be a natural way to probe this era between the end of inflation up to the start of BBN. So we want to look at how gravitational waves can help us looking at some physical phenomena which can happen in pre-BBN universe. So to give a brief outlook of what our setup is, so we consider a hidden sector which is thermally decoupled with the Standard Model. So hidden sector has a temperature TH and Standard Model has a temperature T Standard Model. And we also assume that the Standard Model makes up the bulk of the energy density of the universe. And from now onwards, I will quantify the ratio of the hidden sector temperature with respect to the Standard Model as chi. And for the purpose of this talk, I will assume that my chi is less than or equal to 1. So overall, the net energy density of the universe in the radiation era will be given by the sum of the two energy densities of the hidden sector and the Standard Model. So here G star H represents the relativistic degrees of freedom for the hidden sector, and G star Standard Model represents the degrees of freedom for the Standard Model. And T from now on will represent the temperature of the hidden sector. So if you want the temperature of Standard Model, that is given by T by chi. So now what we want to look at is that suppose in the early universe, if there are any energy injections before the BBN. So in the past, people have talked about such scenarios in a variety of different approaches. So one of the ways it can happen is via the fluctuation entry during, so the fluctuations that are generated during inflation and they enter the horizon later. Another way is that if there are initially some domain walls lying around and then they collapse, that can lead to some energy injection. People have also considered PBHs in the early universe, which can then evaporate and reheat the universe. There are also possibilities of bubble collisions during phase transitions. Another way to get some energy injection is via temperature increasing during the reheating. And people have also considered scenarios where we have some moduli fields in early universe and then they decay and heat up the Standard Model and any other bath. So there are like different ways, and I will be focusing on two concrete examples of the PBH reheating and the modular decay to show that there is some quantitative estimates of this energy injection. And also for our talk, we will consider the rate of the energy injection to be fast such that the hidden sector field will remain stuck at its temperature as the temperature rises. So the rate of change of temperature is faster than the phi change. So to quantitatively show what happens when there is an energy injection. So firstly, since we have this hierarchy in the two sectors, any small change in the energy density of the universe will lead to larger impact for the hidden sector as compared to the Standard Model. So the T of the, let's say of the hidden sector, after the energy injection will go to T tilde, which is given by T1 plus delta. So delta will quantify the amount of energy injection that I have. And if there are any possibilities of phase transitions in the hidden sector, then this can lead to multiple phase transitions, and which can leave its imprint on the gravitational wave spectrum. And a condition that we will put on the product of chi and 1 plus delta is that we want the Standard Model to be dominant over the hidden sector. So overall, you can solve and you get a constraint on chi times 1 plus delta to be less than the ratios of the G stars of the Standard Model and the hidden sector raised to power 1 by 4. So depending on the temperature, this is more or less order 1-ish. So that this gives an upper bound on how much energy density you can input without the hidden sector becoming the dominant part of the total energy budget. So first example is via modular decay. So suppose if there is some moduli fields lying around and they only couple to the hidden sector. So then when the decay rate of the chi, let's say it's a chi field, it becomes equal to the Hubble at that temperature, then it can undergo decay. And so we can write down the energy conservation equation before and after the decay. So rho h prime is the energy of the hidden sector after the modular fields decay. And this is equal to the sum of the energy density in the hidden sector and the rho of chi. So when you solve this, you find that the Th prime, which is the hidden sector temperature after the modular field decays, is equal to Th 1 plus a ratio of the energy associated in the modular field divided by the energy in the hidden sector. So as an example, if suppose the hidden sector temperature scale is roughly 100 GeV, so then for m chi of 10 to the 8 GeV and an initial field value of 10 to the minus 5 GeV, the delta value you can get is around 0.4. Similarly, if you have a larger chi value, let's say of 10 to the minus 4 GeV, then the delta will be order 3. So this is one example of how you can get some energy injection in early universe. Another scenario is like, suppose if you have some light PBHs lying around in the early universe, then once they evaporate, they can lead to an increase in the temperature of both the Standard Model and the hidden sector. And when you solve the energy conservation equation before and after the evaporation, you find these two relationships. So T prime Standard Model is given in terms of T Standard Model, 1 plus eta times T naught over T Standard Model. And as you see here, these two terms in the brackets, they are similar, but since the TH is smaller than the T Standard Model, the relative effect on the Standard Model is much smaller than the effect on the hidden sector. And eta here corresponds to the initial mass fraction of the PBH. So again, just if you want some numbers, so if your hidden sector is of the 100 GeV energy, scale, then a delta can be 0.45 for a eta of 10 to the minus 11 and a chi of 0.1, and where the PBH mass is roughly 10 to the 4 grams. For a larger energy dumping for the same mass of the PBH, then you need a larger eta, which is here roughly 10 to the minus 9. So this is like another example where you can have some amount of energy injection into the early universe. So now we have like some energy injection which is possible, as I show in the previous slides. So now what we want to do is like we want to study its impact on the hidden sector, and for concreteness, we consider polynomial-like potentials as our case study. The reason is that for polynomial-like potentials, you can do good analytical estimates for the phase transition parameters and also calculate the associated gravitational wave spectrum. So here I show a usual polynomial-like potential, and in the standard story, at a very high temperature, initially the potential is symmetric, and it's like the field is in a symmetric phase, and there is only one minima, which is at phi equal to 0. Now, as the universe expands, when the t becomes less than t1, there exists a second minima, which is given by phi 1, which is non-zero. As the universe further cools down, we reach the critical temperature, which means that the phi equal to 0 minima and phi equal to Tc, they are equipotential. So you can solve these guys and then get the corresponding critical temperature and the critical field value in terms of the model parameters. As the universe further cools down, the temperature becomes smaller and smaller, and phi equal to 0 actually becomes a maxima. So you are left with a single non-zero minima, which is given here. So this is the standard story. So for us, since there is some energy injection, what it implies is that it can lead to the reheating of the hidden sector, which can lead to multiple phase transitions. So for the situations I want to describe, we can have 3 transitions instead of just single transition. And to put mathematically, what it implies is that if there is energy injection, which happens anytime after the temperature is equal to T critical, so let's say it is happening at Ti. So then, and as long as Ti 1 plus delta is less than T1, if the energy injection happens anywhere above here, then it won't really lead to any new transitions, just because it will keep the shape of the potential similar. So as long as you have these 3 constraints working, you can have 3 transitions. And in terms of the model parameters, it is nice to quantify the model dependence in terms of this eta variable, which I defined as a ratio of lambda d by e square. So for a standard scenario, eta is always lower bounded by 9 by 4. once you plug in these three conditions and you solve them, then you also get an upper bound on the eta, which is 9/2. So from now onwards, I will keep eta as my parameter to think about the model dependencies. And for a corresponding value of eta, then you can choose your values of lambda, d, and e to get a particular class of model. So as I said earlier, for the phase 1, which is the standard scenario for phase transition, when the potential becomes equipotential, like the two minima are equipotential, then initially the field is lying somewhere here, and then it undergoes a phase transition, and it goes to the blue dot here. For the phase 2, which is the new phase, initially we had the blue curve, and field was lying somewhere at a t-dependent minima. Now, due to the energy injection, the potential actually takes the shape of the red curve, and now we roll to this red point. Now, as you can see that this minima is not the global minima anymore, and it will undergo a phase transition, which is in the opposite direction to the usual transition. So we are going from a broken phase to a symmetric phase. So this is what I term as phase 2. Now, as the universe expands further and cools down, the potential will again take the shape that it took for the phase 1. So the phase 3 is the same transition as the phase 1, but it only happens at a later redshift. So to put it all together, the picture is that on the y-axis we have the Hubble, on the x-axis we have the standard model temperature. And since I said that my energy injection, as long as it is small, it won't really change the Hubble rate too much. So initially in the standard scenario, we have this phase 1, which is the standard transition. Now, depending on the amount of the energy injection, which is proportional to delta, we will have the phase 2, which is the inverse transition, and then again the phase 3. And how far they are separated along the Hubble depends on how much is the energy injected. So this is like the picture that we have. So since I choose my potential to be a polynomial-like, I can use the known results in the literature. So one result by Fred Adams, he showed that one can write down the Euclidean action, which determines the tunneling rate from a false to a true vacuum via some analytical forms. So basically the S3 over T parameter can be expressed in terms of the model parameters E by lambda raised to 3/2 times a functional form Fs. And here important quantity is this kappa, which is proportional to the model parameter eta here, and then times 1 minus t naught square by Tn square. And importantly, kappa lies between 0 to 2. When kappa is close to 2, the transition is very fast. If it's like very small, like closer to 0, then it might enter into the supercooled region. Now, once we have this, so these expressions are true for the phase 1 and phase 3 because they are the standard expressions. So for our phase 2, since the transition is in the opposite direction and it's slightly different, we had to do a slight remodification, like redefinition of the fields, and one can rewrite the potential which expresses the transition from a broken to a symmetric phase in terms of new parameters d tilde and e tilde, and they can be expressed in terms of the parameters d and e times the kappa of T tilde I, where T tilde I is defined as Ti 1 plus delta, where Ti was the temperature at which the injection happened. And similarly, you can define the new parameter kappa tilde, and this can also be expressed in terms of the kappa parameter times a function of kappa of Ti tilde. So now, this means that we have like this Euclidean action for both the phase 1, phase 3, as well as phase 2 in terms of our model parameters, as well as the amount of energy injected. So now, once we have the S3 over T, then we can define our nucleation temperature, which is defined as the temperature where basically a true vacuum bubble arises within the Hubble volume. So roughly, this is given by this equation gamma over h raised to 4, roughly equal to 1. So one can simplify it further by taking this functional form of gamma in terms of S3 over T. So here, my S3 over T with the index j, so j corresponds to phase 1, 2, and 3, is given by an order 100 number. And then this is the G star, which is the relativistic degrees of freedom. The chi, which is the ratio of the standard model with respect to the hidden sector. The T naught is the scale. And then we have the model dependence. So as you can see, all these terms are log dependent. So even if you change the chi values and the model parameters slightly, the effect on the S3 over T will not be drastic. So we find that the S3 over T for all the three transitions is of the order 100. And once you know what S3 over T is, then you can also define the rate of transition in terms of beta over H, which is given as a derivative of S3 over T with respect to the log of temperature. Similarly, we can also define the strength of the phase transition, which is given by alpha parameter, and this is defined as the difference between the V minus derivative of V with respect to T by 4 between the false vacuum and the true vacuum, and weighted by the total radiation energy density. So the larger the alpha is, the stronger the transition is, and vice versa. And for wall velocity, we use an analytical approximation, which has been described in a lot of literature, also in a lot of work by John Ellis. So here we use a very simple form of the Joge velocity, which is given in terms of alpha. And as long as this parameter delta V by alpha rho r is less than root Vj, we take it to be this value. And if it's greater, then we take it to be 1. So this is a place which is a bit crude approximation, but I think to do a better job, one needs slightly better numerical simulations. So then once we have all these phase transition parameters, then we can try to calculate what is the associated gravitational wave signal, which comes from the first order phase transition that we described earlier. So we use, firstly, we define this gravitational wave density parameter in terms of the derivative of the energy density of the gravitational wave with respect to the log of frequency, and it weighted by the critical energy density. And we use the semi-analytical parameterizations where we sum over all the three contributions coming from the bubble wall, the sound wave, and the turbulence. And here corresponds to the normalization factor, delta I corresponds to the velocity suppression factor, kappa I is the efficiency factor, alpha is the strength, Pi, Qi are the exponents, and beta over H is the rate of transition. And Si is the spectral function. And for F equal to Fp, it becomes 1, and for other values, it's smaller. So this is the gravitational wave amplitude at the point of emission. And then one has to do, to get the value today, we have to do some redshifting. So we have a value R, which is roughly 10 to minus 5, which takes into account of the redshift. And also one has to redshift the frequency. So now, like just to recap the general features of the hidden sector phase transitions. So firstly, the alpha parameter, which is the strength, it's proportional to chi raised to R4, which was the ratio of the hidden over the standard model. So the larger the chi is, the stronger the gravitational wave signal will be. Larger beta implies faster transitions, which lead to signals which are weaker and they peak at higher frequencies versus the slower transitions. Larger wall velocity implies smaller peak frequency and larger gravitational wave amplitude. Smaller nucleation temperature will lead to lesser redshift suppression, which implies the overall signal to be stronger. And smaller Tn over Tc is an indication of how long-lasting the phase transition is. Also, so right now it looks like the three phases are kind of independent, but we saw that the phase 1 and phase 3, as it was discussed earlier, they only differ that they happen at different redshifts. So fundamentally, in their like mathematics, they are similar. So the kappa parameter, which quantifies all the phase transition parameters for kappa 3 and kappa 1, they are roughly the same. So what we found is that the phase transition kappa for phase 3 is equal to kappa 1 plus some small parameter chi, which is given by this quantity, which is proportional to log of 1 plus delta. And this is less than 1 because this is a ratio of 8 over order 100 times order 10. And what this means is that now we can relate the alpha, beta, and other parameters between the phase 1 and phase 3, and which leads to the ratio of the peak frequency of phase 3 over the peak frequency of phase 1 to be roughly order 1. To be more precise, this is given by log 1 plus a log of 1 plus delta. So the amount of energy injection doesn't really change how far the two peak frequencies lie. For the phase 2 and phase 3, the expressions are slightly more complicated, and this is because the phase 2 is fundamentally different than the phase 3, because phase 2 goes in the opposite direction from a broken phase to a symmetric phase. So what we found is that the peak frequency ratio for phase 2 with respect to phase 3 is given by a kappa I dependent functional form times the model dependence, and this is less than or equal to 1. And what one can also do is, because we know the bounds on eta and kappa for the polymer-like potentials, then we can find the maximum amount of separation that you can have for the peak frequency 2 versus peak frequency 3. And this is roughly an order of magnitude. So you can't do better than separating the two phases by more than, let's say, an order of magnitude. So overall, the important part here is that the cosmology, which is given by the delta and the chi, that is more important rather than the details of the model. Even if you had some other model beyond a polynomial-like potential, the hardship would have been in calculating things analytically, but the overall picture should still work. So but at least for our case, what we also found is that the amplitude of gravitational wave for phase 1 and phase 3, they are also related in terms of delta. So the peak frequency for phase 3 with respect to phase 1 is given by 1 plus delta raised to R6 times order 1 number. So for larger delta, the overall amplitudes will be further separated, and for very small delta, they will be on top of each other as we expect. For phase 2 and phase 3, I cannot write down a very closed form answer here, and the reason again is because the omega, the functional form of omega for phase 2 has contributions which have different functional forms with respect to the bubble wall and the sound wave, because it's a different phase transition versus the phase 3. But the overall, it scales proportionally to the model parameter eta in addition to the chi and delta. And also knowing the peak frequency difference between phase 2 and phase 3 leads to a value of the chi 1 plus delta term in terms of model parameters and the scale of the hidden sector. So now just to show some concrete result. So for this benchmark point, where I choose chi to be order 1-ish, delta to be 0.6, eta, which is the model dependent parameter, is 2.4, and the hidden sector scale to be 450 GV. I'm plotting my h square omega versus the frequency. So the blue curve here is the standard gravitational wave from the phase 1, which we will expect. The green curve is the one which is the phase 3, corresponds to phase 3, and the red is the phase 2. So as you can see, the peak frequency for phase 1 and phase 3, they roughly lie on top of each other, and the difference between the net strength is proportional to 1 plus delta raised to R6, which we checked. And this is plotted for the maximal separation that you can get between the phase 1 or 3 versus the phase 2 in terms of peak frequency. So this is roughly order 10-ish, and this is like maximal you can get, and this happens for kappa values of the order of 1.55 for phase 1 and phase 3 and 1.6 for phase 2. So similarly, you can also change the values of the chi parameter, the eta parameter, and T0 parameter. You will still find that the scaling still work out the same. So again, I have the values of kappa which gives the maximal separation. So 1.5 for phase 1, 1.6 for phase 2, and 1.55 for phase 3. These two lines are for different deltas. And as expected, the beta over h values for phase 1 and phase 3, they are roughly the same, and they don't really change that much by delta. And phase 2 is inherently different, as you can see in the beta over h values, and it followed also from the analytical expressions that we have for the beta over h ratios. And for increasing delta, the omega value increases as we expected. So just to discuss basically what are the takeaways. The energy injection delta, it plays a very important role in shaping these gravitational wave features, and larger energy injections, this will lead to stronger gravitational wave amplitudes in phase 2 and 3 as compared to phase 1. And this is primarily due to the smaller redshift suppressions. So the table also verified that the peak frequencies for 1 and 3, they are similar and they differ from 1 by a factor of log 1 plus delta. And the omega p ratios, we checked that the table also shows that the scaling is 1 plus delta raised to R6. And for smaller chi values, the peak amplitude becomes smaller due to the weaker phase transition strength, which is given by alpha, which was proportional to chi raised to 4. So to conclude, the idea here was a very simple framework in which if there is some energy injection, either via PBH or modular decay or any other method that you like, then this can lead to the hidden sector temperature going from TH to TH1 plus delta. And if the hidden sector had a capacity of having some phase transition, then this can lead to a multiple phase transitions which are correlated and which can show up in the overall gravitational wave spectrum as the 3 gravitational wave peaks. And it is also fairly independent with respect to the mass scale of the hidden sector. The benchmarks I choose were just arbitrary, but one can also choose higher values of the masses or smaller values of masses, and this will shift the overall peak frequencies in the directions. For the smaller masses, it will go for like smaller frequencies. And overall, the hidden sectors with the gravitational wave, they can probe a variety of new physics scenarios in the pre-BBN era. So I think this is all I had to say. Thank you.
Okay, please. I think in this phase 2, the latent heat might actually be negative. Did you encounter the latent heat or alpha?
Yeah, so for phase 2, the latent heat is negative, but then the pressure difference due to the masses, since they go from a broken to a symmetric phase, that is also negative, and that is the one which drives the overall bubbles.
Right, but I think the alpha, as you define it, also will be negative.
Yeah, so the alpha, like the overall alpha, if you define that will be negative, so the driving force will be negative. So it means that the friction for the bubble walls for the phase 2 is due to the mass difference instead of the latent heat.
Yeah, no, I'm just saying when you calculate the gravitational waves, so how do you get out the kinetic energy? Meaning
yeah.
Exactly. So the kappa is typically in the literature, people only quote kappa for positive alpha, right?
Yeah. So I think like there was a paper last year by some people who studied this inverse transitions, and then from there we use the value of the kappa for this inverse transition.
Yeah, I remember there was a paper by Simone Blasi.
Yeah.
So that's what you're using.
Yeah. So basically, I use their kappa values for the alpha.
Okay, cool. Thanks.
Let's go ahead.
So can you go back to the initial slide where you introduced the potential form? Yeah, here. So for the phase transition from 1 to 2, you're using this model kind of potential due to the energy injection, if I understand correctly, right?
Yeah, so I'm starting with this potential form because like it is easy to calculate for these forms. So at this point, I have not used any injection. So this is just like a standard potential for like a Mexican height potential plus the thermal corrections.
Yeah, so this particular thermal correction term comes in the one loop approximation.
Yes.
So in that very high temperature limit where you're going from a broken phase to a symmetric phase again, does that one loop correction approximation is still valid?
Yeah.
You can use this.
Yes. I think like this should be, yeah, so I like at this level it should be working because all I can do is that I can just start with my specific model of the hidden sector and then I can write down the JB and the JF functions which correspond to the like the T raised to 4 by 2 pi square JB of whatever fields I have. Plus
right, but that JB and JF will come from the one loop approximation.
Yes.
So, I mean, if the one loop contributions are not significant, like there would be second two loop contributions which can play a role.
Yeah, so like for my study, I've like limited myself for like to say like in a sense to the one loop approximation. So if there is a scenario where the one loop's contributions are subdominant, then I'm not sure like what the overall functional form will look like. So basically, then I don't think you can use this kind of setup. So this is like overall, if you start with a one loop approximation, the functional form will look like this, and as long as the functional form looks like this, then you can use the basically these results. So in this paper, the functional form is of the type of a polynomial-like potential. So here I'm just like coupling it to the hidden sector as an example to only change the temperature of the hidden sector. And also since like my hidden sector and model, I've assumed them to be like, let's say decoupled or very minimal coupling. So I'm not sure like if I can, like I'm considering the scenarios where it couples to like both the things and what is the strength. It's basically like I'm assuming that chi couples to the phi to my hidden sector and then it just gives the energy once the gamma chi is roughly equal to the Hubble. Yeah, so I think like in those scenarios, basically like, so this is like a very simple approximation of getting the delta value out. But in any other scenario, I think like I will have to put some kind of a functional form on delta, and then I think the calculation will be much more involved. So here I'm just assuming that the delta is like the energy which it pumps is very fast, it's rapid, and all I want is like some value of delta.
Any further questions, comments? Okay, so if that's not the case, so let's close the session and also for the day. So it was a long, hectic day, I believe. So we need some well-deserved rest. So tomorrow we resume at 9:30 with Mars talk. Thank you very much.